about that. This makes it extremely difficult to manage the risks that are created by existing underground utilities. This is a fact of life. The design engineer is not responsible for having the information of getting the information of the underground utilities, because it is supposed to come from the client. Client gets it from the old records. Contractor does the work as per the design, etc., etc. So ultimately, at the end of it, no one is answerable. So the problem is that there is no central repository for location of underground utilities. There is no single database from where you can get the location of underground utilities. No single agency monitoring the laying of new utilities. Non-availability of as-built drawings. We know very well that as-built drawings more often than not are replica of as-designed drawings. We will not go in detail why is the case there. And covering of manholes and inspection covers during laying of roads or relaying of roads basically eliminates practically all the signatures of utilities on the ground. So with this limited or almost no information, the design is carried out and even the construction starts. And then if we feel that we are a smart decision maker, well, we are a smart decision maker with our eyes closed. So why we need smart solutions? First, we don't know where most utilities are. Second, the existing records are often inaccurate or incomplete. Third, risks become extremely difficult to manage under such situation. And what are the risks? Project delays, damage to utilities, safety of workers, safety of public, redesign costs, change orders, bad publicity. All these are the risks which we are dealing with. So what is the answer? So now let's look at the answer. Before we look at the answer, I would like to understand, in your opinion, which is the most suitable or appropriate method or procedure to create maps of underground utilities? Ground penetrating radar, electronic pipe locators or induction locators, trenching or other? Of course, you will not be able to answer this question, but with my experience of doing this lecture live, the kind of answers I get, 42% say GPR, around 22% say EPL, and 27% say trenching, and around 9% say other. So that's the kind of response which we get. I will come back to this question at the end of this presentation again. So what actually is the answer? So the answer is new technologies for solutions, surface geophysics, surveying techniques, CAD and GIS, minimally intrusive excavation, all this. Convergence and systematic use of this data, and that is what we call SUE, Subsurface Utility Engineering. Now before I go forward on this, let me just tell you one thing. This entire concept of SUE started in US. Okay, that's right. So whatever we have talked about, the data not being available or data being inaccurate, etc., etc., this was felt in US in their transportation sector, and that's where they came up with the concept of SUE. So we are not talking about India. We are talking of a country which is supposed to have very good utility network, very well defined utility network. Despite that, they realize that if they are trusting only the data which is available, they are meeting with lots of problems, and that's how they came up with the concept of SUE. So what is SUE? What is subsurface utility engineering? So it is a proven process that incorporates new and existing technologies to accurately map underground utilities during the development of future construction projects. It encompasses several separate activities including designating, locating, surveying and mapping, all of which are performed under a professional program of data management. The essence of subsurface utility engineering is simple. Before an engineer designs a project involving excavation, the engineer should know what structures and conditions are beneath the earth and where they are in 3 dimensions. Such structures are usually utilities but may include underground storage tanks, septic fields and other things. That is basically what SUE is. It is use of new and existing technologies to accurately map underground infrastructure before you design a construction project or you execute a construction project. So it involves collection of underground utility data and the use of that data by the right parties at the right time. Its major components is designating, locating, surveying and mapping, and data management can be defined in terms of quality level of information. Now this quality level of information is the main thing which goes behind SUE. We will look in great detail. So quality level may be thought of as degrees of risk or how much information is really needed before planning, designing and constructing a project. So quality level, as the name indicates, it will tell you the quality of the information which is available. At the same time, what quality of information is required will depend on what stage of the project you are on. The importance of the concept of quality level will become very clear very soon. But if we look at the everyday life, we meet different kind of people. Now, it's not written on anyone's head, how reliable that person is. And that is the problem, right? If we knew, for example, that, this person is 100% reliable, this is 75% reliable, this is unreliable, we will never be cheated in life. Life will be so simple. But that is the concept, that what we are trying to do in SUE, that each information we are trying to give a particular label to the information so that we very clearly know what is the reliability of the information. So now let's go to this. This is the kind of maps we generally have available, the old maps. Now this is a simple ammonia blueprint. There are various roads here, and on these roads different color pens have been used to show different utilities. Now once you look at this particular map, there is no problem at all. You know that this particular color just shows that there is one particular line on this road somewhere. You will never try to try to take a judgment that this line is on the left or the right or the center of the road, because the tip of the sketch pen is as thick as the thickness of your road. No problems with this map. It is just a schematic to show that there are different pipelines on different parts of the road. So where the problem starts? Problem starts that when we are giving a map today, let's say we are given a beautiful printed CAD map. Do we have information on reliability level of these maps? Does the map mention anywhere that you can rely it 100% or 50% or 25%? Answer is no. Do we have information on data used for map preparation? How the map has been generated? The answer is no. Now the problem is that this kind of map, this kind of ammonia print which I had just shown you earlier, sometimes it is given for digitization. So it is given to, let's say, a CAD operator, and he starts digitizing this map. He puts these roads which are just 1 millimeter
on geophysical methods for pipeline rehabilitation projects.
In CAD, he will put these roads 20 meters
I am
apart.
Sanjay Rana. I am managing director of Part1.
I am a professional left, right, or center, depending on his judgment. Okay, so the information which was not there has been created during digitization,
and it's also used to
ultimately
detect
now
the
this
leak.
map will be given to you for your design purpose, and you will blow it up. You will try to see what is the distance of this pipeline from the road edge. Okay, it is 2 meters from the road edge. The information actually never existed. It has been just created in the process of digitization, and the map nowhere mentions that this map has been just created by digitization of a blueprint and should not be trusted for accurate location. No map ever gives you the reliability you can have on that. That's the problem. So SUE establishes nomenclature system to fix attribute to utility information to denote quality of utility information. That's the major thing in SUE. It basically develops establishes a nomenclature system which fix attributes to utility information to denote quality. What is the quality of the information? There are standards, of course, which deal with how information can be obtained, what technologies are available, how information can be conveyed to information users, etc. Intent is to reduce risk by improving the reliability of information on existing subsurface utilities in a defined manner. So now, once you are coming down, you know how much you can trust these people to actually hold you. There are certain definitions which are slightly different than what we generally understand. So it's important to designating is use of geophysics for presence and approximate position. Locating is exposing and recording precise vertical and horizontal location. There are so many practitioners who use the word locating for finding out underground utilities using GPR or induction locators. In terms of SUE, that is not locating, that is designating. Locating is only when we expose it. Then minimally intrusive excavation like
welcome to
vacuum
this
excavation,
guest
water
star
jet, careful
of
hand tool
working.
uses.
So
Subsurface utility
you
engineer, a
can't
person who by
sit
education and
tradition
experience is
the best
qualified
way
to
forward
practice SUE.
that trenchless
Utility
technology can
depiction
help
is a
with.
visual image of
So thank you
existing
for listening.
information using a
There's
CAD
my
system or
contact
drafting
details,
system.
and
And most important, utility quality level. This is the opinion of quality and reliability of utility information. This you can say is the main aspect of the entire SUE process. That each and every utility must have an associated utility quality level. That all the information which is being provided to the user must know how much he can trust that information.
thing that was most likely to let down.
So there are different quality levels. Quality level D is information gathered solely from existing utility records. This is mostly what was being done till recently and is still being done in so many cases. So you just go to your old records, take out that information, and based on that make a utility composite and now use it for design. That is quality level D, the least reliable system, the least reliable quality level. Then comes quality level C, that now you had got a old drawing which was showing sewer lines somewhere on the road. Now you send your surveyors on the ground. They pick up the visible above ground utility facilities and appurtenances like manholes, like water walls, like junction boxes, etc. And now align the utilities known to be there through quality level D with the surface appurtenances. So this becomes quality level C data. This is definitely better in terms of reliability than quality level D, but still nowhere reliable enough to get into design or construction phase. Then comes quality level B. This is where it deviates the most from our traditional approach. This is where the major change is. It uses surface geophysical techniques to determine the existence and horizontal position of underground utilities. So here geophysical surveys come. Here, for example, GPR comes, induction locators come, electromagnetic surveys might come, magnetic surveys might come, etc., etc. There are a number of techniques which have been listed in terms of geophysical techniques which can be used for underground detection of utilities. Fact remains that there will be maximum 3 or 4 which can actually be used in urban environment. And last is quality level A, which employs non-destructive digging equipment at critical points to determine the precise horizontal and vertical position as well as size and type of underground utilities. That's very important to understand that even after this, it's not 100%. Quality level B does not give you everything. For example, GPR or any such technique does not give you size of the utility, the diameter of the utility, or the material of the utility, for example. Okay, so you have to go to quality level A if your project requires that kind of information requirement. There are standards like ASCE. This is one of the oldest standard by American Society of Civil Engineers. Then PAS 128. This is British, of course. Now the unique nature of utilities and record keeping in different countries necessitate various changes in the SUE approach. So in India, with INDSTT worked on this and came up with this code of practice for subsurface utility engineering suiting Indian condition, and it was brought out in 2018. So very briefly, I'll discuss about different quality levels. So as I said, quality level D is the most basic and the least desirable level of data. It comes solely from available utility owners' information. It has application for planning purposes such as selecting routes and estimating utility relocation cost. Now, very important note, this also has application. It's not useless, but for initial planning, pre-feasibility studies. Even though quality level D information may provide an overall feel for the congestion of utilities, it is highly limited in terms of comprehensiveness and accuracy for design purposes. So you cannot use it for design purposes. Can use it for pre-feasibility studies. So this is usually adequate for route selection, but make no mistake, this level of data is not adequate for design purposes. So it comes from record research, recollections, as-built drawings. This is the source of quality level D data. So this is, for example, Faridabad, the ULB map for master sewer plan. This will be a quality level D data. This again shows presence of pipelines, all these green lines. This will be the quality level D data. This is a map showing mid part of Hyderabad ULB's main supply line and overhead tanks. This is quality level D data. So this is the data which is very important to gather, of course, because this gives you a good start point for your further work, but this is not good for design purpose. Now, source of errors, of course, data is not referenced to change topographical features. For example, a pipe on side of the road comes in center when road is widened. Inaccuracy creeps in if utility layers are not referenced to MSL. So, for example, a pipe at depth of 1 meter will go to a depth of 1.2 meter with 20 centimeter road top added. As designed are mostly reproduced as built. So, quality level D, of course, as I said, is the least reliable source of data. Next comes quality level C. Historically, quality level C was probably the most commonly used level of information for design purposes. It involves supplementing quality level D information with an above ground survey of visible utility features such as manholes or wall boxes. Utility records and topside survey data are just not enough to provide an accurate picture of where subsurface utilities are located. Professional studies have shown a 30% error or omission rate with this approach. So, quality level C should rarely be used for design purposes when underground utilities are present. So, it's definitely an improvement on quality level D, but again, not good enough for design or construction. Here, this is mapping of surface utility features. You can use total station or DGPS, and that is what comes in quality level C. Then comes quality level B. So, quality level B is the first level where subsurface utility data departs from traditional practices. It involves supplementing quality level D information with designating, surveying, and mapping. Designating is the use of surface geophysical technologies to determine the existence of underground utilities in plan view. The use of this information allows decisions to be made during the preliminary design phase of the project in order to avoid conflicts with existing utilities. Slight adjustments in the design can produce substantial cost saving and increase safety by eliminating utility relocation and moving excavation work away from existing utilities. So this is where the major improvement comes in the entire process of detection and mapping of underground utilities. Now there are most commonly used tools. As I said, if you really go to the list, there will be more than 17 to 19 different methods which are listed. But fact is that in urban environment, the most commonly used tools are GPR, ground penetrating radar. This can detect both metallic and non-metallic utilities. It of course has capabilities and limitations. This session is too short to go in detail of it. Idea is just to give you an overview of SUV. There are few videos which are referred here. You are more than welcome to watch these videos. Second most commonly used tool is induction locator. GPR was working on the principle of electromagnetic reflection. Here we are working on the principle of electromagnetic induction. So again, this is very good for detection of metallic utilities, for detection of electrical cables, etc. It cannot detect non-metallic unless there is a tracer wire inside. Again, a different subject. But this is a separate second most commonly used tool. Then we have acoustic locators, which are used to detect very small water house connections, etc., which cannot be detected using GPR because of size issues. And we have separate gas pipeline locators. There are references here where you can go and look in details of all these techniques. So this is what comes under quality level B. And the next is quality level A. So quality level A information is the highest level of accuracy currently available. It involves adding locating to the quality level B information. Locating is the exposing of the buried utilities to determine their precise horizontal and vertical position in plan and profile view. So now we are not just working on the principle of, let's say, two-way travel time like we were doing in the quality level B, but actually we are exposing at particular position and inspecting the utilities. The use of non-destructive vacuum excavation equipment and other technologies eliminate damage to underground facilities. You cannot, for example, excavate using JCB or mechanized equipment. It has to be using non-destructive equipment. The small test hole reduces impact on traffic. Test hole is 20 centimeters by 20 centimeters, so it reduces pavement damages. So by knowing exactly where a utility is positioned in 3 dimensions, the designer can also make small adjustments to the final design elevation, horizontal location, or structure types to further avoid relocating utilities or digging near them. The engineer also gets critical data about utility condition, size, material types, soil conditions, and other important information, since you are actually digging and exposing the utilities. So this becomes, in a way, guarantee in 3D. So there are vacuum excavations, there are air vacuum excavation, there are water jet excavation, etc. We can also, open the existing manholes and chambers. So this is one case. So this is, for example, power cable, then this is water pipeline, and this is the open chamber. So if you take the utility data using this also, it comes into quality level A. Again, you can have a video look at vacuum excavation, how it looks like. This is a very good video which is there. I have given a reference here. Ultimately, putting this all information together, we make subsurface utility maps. And well, depending on the project, we decide how these maps should be printed. But the fact is that any map becomes a subsurface utility map prepared using the process of subsurface utility engineering only and only if every utility has an associated quality level. If utilities are not having associated quality level, it is not an acceptable SUE map. So for example, this is a legend where different utilities have been shown, and here notes quality level A data point indicate by symbol this, elevations this, etc. So the point is that every utility should have an associated quality level, and then only it's a SUE map. Look at this map. This is from Mumbai. Yeah, this is from Mumbai, and you can see different utilities, and every utility will have an associated quality. This is the cable, quality level B, quality level B, quality level B. It means it has been detected using geophysics, etc. So this is the way a SUE map will always have an associated quality level. Now, SUE doesn't need to follow a set pattern. It is tailored for individual projects, so it's not a fixed pattern, but it involves systematically identifying the quality of utility information needed to design a project and acquiring and managing that level of information. So, for example, project planning, as I said, quality level D is sometimes good enough just for the initial project planning. Once you go to preliminary design, you can have completely go for quality level B data, no problem with that. But once you are going for final design and ultimately into construction, you have to have some test holes and related utility data. That means you must elevate your information to quality level A. So this is a proven solution. In many countries, it has been proven and given great results. These, of course, need for standardization. So first is procurement, of course. Be aware of false knowledge. It's more dangerous than ignorance. So how you engage a SUE provider is as important as whether you engage one at all, because an inaccurate subsurface utility engineering data is as dangerous and at times more than no data. So SUE service provider should be responsible for accuracy and reliability of the data delivered. Accountability is the key. Written quality assurance procedures, it's an interpretive science, so experience is critical. Equipment inventory is very important because no single equipment can provide all the information. So you need to have GPR, you need to have acoustic locators, you need to have induction locators, etc. There should be internal CAD capabilities and, of course, timely performance. So multidisciplinary approach. So the team should be a mix of geophysicists, surveyors, and CAD engineers, etc. This is basically the combination of SUE engineer, CAD engineer, utility engineer, geophysicist, survey engineer. So this is a stamp which I will talk about it later, but this actually is the person who can be called an SUE engineer. The Indian standards deal with what SUE engineer is. It deals with survey grades, level links to MSL, coordinate system, use of multiple technologies, clear identification of quality levels, experience, manpower, equipment, etc. Now, after going through again, I'll go to the same question. In your opinion, which is the most suitable, appropriate method or procedure to create accurate maps of underground utilities? And now, once I ask this question, around 96% people finally say it's subsurface utility engineering. So it is not GPR, it is not EPR, it is not trenching, it is SUE. GPR is nothing but a small part of SUE. So it's just one of the tools which should be used for detection of utilities and not 100% relied on. If you want to learn more about SUE, INDSTT is offering this SUE course with different modules, right from introduction to SUE to quality level D and C, B and A. This course is being jointly offered by INDSTT and AF Academy. And this is learning with certification. It's online through learning management system. So all the videos are there on the learning management system. The reading material is provided and you basically have to go through these videos. So this comprehensive course covering all the aspects of subsurface utility engineering like GPR, EPL, etc. with detailed description of data processing also. This is the only course which takes the learner through basics of SUE, data collection procedure for QLD and C, detailed procedure for QLB data collection using GPR, induction locator, acoustic locator, etc. QLA procedures including vacuum excavation, instruction of drawings preparation, etc. Upon successful participation, the participant would be awarded SUE engineer certificate with uniquely numbered stamp. This is the uniquely numbered stamp. Every stamp has a number to sign and certify underground utility drawings. There are less than 100 certified SUE engineers in India at present. The training program is approved by Engineering Council of India for the award of 224 continued professional development hours. With this, I come to the conclusion of this particular presentation on subsurface utility engineering. I would love to take your questions and thank you very much for your attention. Here is my email ID and my number. Please feel free to contact me for any queries. Thank you very much. Welcome to this presentation on geophysical methods for pipeline rehabilitation projects. I am Sanjay Rana. I am Managing Director of Part1. I am a professional geophysicist with 30 years of work experience. I graduated from University of Roorkee, which is now IIT Roorkee. I am a member of various working committees for development of codes and practices and standards, including IRC. I also frequently conduct training programs on use of geophysics for various applications. And I have the privilege of initiating the concept of SUE in India in 2001 and geophysical investigation across flowing rivers, dam geophysics, passive seismic tomography, etc. I represent the company Part1, which is an ISO certified company. We are the largest engineering geophysics company in the country, but more than that, we are known for the innovations we have been bringing in the country since 1996, when we introduced the concept of ground penetrating radar in India, the 97 shear wave seismic refraction, and the list goes on. And we are the leading and most experienced company in India in the field of near surface geophysics, including SUE. Our main strength is our people who are highly experienced and trained. We have offices in Delhi, Bhopal, Kolkata, and Bahrain, and in Saudi Arabia we are working with associates. And we have work experience of more than 14 countries around the world. Now, coming to geophysical investigations, I would just very briefly like to introduce the concept of geophysical investigations. So as we all are familiar with these images, they are basically medical images. We have, for example, ultrasound and X-ray and MRI and CT scan. And what we are doing here is sending different kind of rays and waves inside the body to capture the image of what's inside the body. That's what we are doing here. Now compare these images with the images here. These are the images created using geophysics. For example, this is a shear zone in an otherwise good bedrock created using electrical resistivity imaging. These are ray bars in a concrete slab created using ground penetrating radar. These are pipes buried under different layers of road created using GPR again. Here you see different layers of soil this is a depth scale, so this has been created using seismic refraction tomography. Here you see boulders, zone of water accumulation, etc. This has been again created using ERI. So we are doing practically the similar kind of work which is being done in medical imaging. Here we are creating the images of the human body using different kind of rays and waves without actually cutting open the body or intruding inside the body. Same thing which we are doing with the earth, without cutting open, without drilling, without trenching to find out what's inside the earth. Our life is slightly more difficult than medical imaging profession for the simple reason that in human body we know what a normal human body looks like. For example, this always is taken as a joint, not as a fracture. But if there was something here, that would have been interpreted as a fracture. So there is something called a normal human body. Unfortunately, there is nothing called a normal earth. Earth changes from one point to the other, and this makes interpretation of geophysical data slightly more complex. Second is that human body is available for 360-degree inspection. You go inside this tunnel and all around you have transmitters and receiver. In case of geophysics, we only have the top surface available for the investigation. So that's the difference. But this is the best point to start understanding what geophysics is. So why to use it? The answer lies right in the comparison which I did earlier. It's always cheaper and faster to get an X-ray done than a surgery. So it's geophysics also low cost, rapid coverage, most importantly continuous information. The traditional way of doing drilling will always miss the isolated objects which are not directly in the drilling path. So drilling gives you only the discrete information, whereas geophysical methods give you continuous information. At the same time, I would like to highlight that geophysics does not replace drilling, it optimizes drilling. So rather than drilling randomly, once you do a good geophysical campaign, you have the continuous picture of the subsurface, and then you only need to drill at the anomaly locations to clearly understand what lies there. So this is the best part about combining and optimizing your drilling with geophysics. It leads to minimization of surprises, because whenever we meet a situation in the subsurface which we did not expect, we call it a geological surprise. Now geophysics helps you overcome that, and it's always good for early stage application for better planning and smooth execution. Now with this very small introduction to geophysics, I will right away go to the topic of the day, that's rehabilitation. So what all challenges we face in rehabilitation? One is the missing link, that is utility location. Sometimes a particular part or segment of utility is not exactly known where it is, and that's what we call missing link. Second is settled pipe. The pipe might have got settled because of defects at some location. Manhole location. As we are covering more and more manholes with the new road layers, sometimes we don't find manholes once we start working. And locating this manhole is a challenge. Then determination of leakage location for pipelines. Then detection of void and cavity along the pipeline. And lastly, pipeline condition assessment. So these are various challenges which are linked with rehabilitation, and I would like to take you through various methods which with few examples, since the total time is around 30 minutes. So I will be a little fast, but you are more than welcome to contact me on any further details. But I like to show you how it works. So first is utility location. Okay, finding out where a particular utility is. So exact location, orientation of utility, and information on missing link is required to be determined for proper planning of rehabilitation works. And for that, there are geophysical solutions, integrated approach of subsurface utility engineering, including tools like GPR, induction locators, acoustic locators, gas pipeline locators, magnetometers, EM surveying, etc. So there are a number of tools and a very well-defined set protocol of subsurface utility engineering which can be used to find out exact location and orientation of utilities for any of these projects. SUE is a subject in itself. There is a separate lecture on SUE which is available, and you can please go through that. Second, settled pipe. There are instances when a pipe settles due to defects or damages or loss of support. It is desirable to pinpoint such location and phenomena. And GPR is able to track the pipe and provide depth to the top of the pipe all along its length. Other supplementary tools can also be used based on site conditions. So for example, this is one very good example that this was a storm drain intake, and the GPR has been done all along the storm drain, and you can see how it is dipping from one end to the other. This is again the cross sections. You see the depth here. Depth here is greater and depth here is greatest. So like this, you are able to track the entire utility from one end to the other and see if there is a settlement of utility at one particular point. This is one very good example of this. This is a GPR profile from data collected along trend directly over top of a drainage pipe in saturated soil. Shows the abrupt transition from water filled pipe, that is west side. So this side is a water filled pipe, to an air filled pipe. This particular portion, east side. The abrupt transition in the GPR response is due to a pipe obstruction that completely blocks the flow of water. So this is a wonderful example of how a complete condition of a pipe has been tracked using GPR. Now the next objective is manhole location. So manholes routinely get buried during relaying of roads. It's of utmost importance to detect these manholes. So geophysical solution for that, manhole location can be determined using various tools, including but not limited to, it depends on the site condition, manhole locators, which you see here. This is one tool which again is working on the principle of almost like a metal detector, but more sophisticated. This is specifically made for manhole locations. GPR again comes in very handy for manhole location, metal detectors, magnetometers, EM surveying, etc. So there are different tools which are available for finding out the location of your manholes which are otherwise not visible, buried under the layer of road, etc. Condition assessment. Now we come to condition assessment. So when we talk about condition assessment, there are different condition assessment methods which we can talk about. We'll list them one by one. So first we are talking with leak detection. So once we talk of leak detection, there are different methods: acoustic, sonic, hydraulic. Okay. So there are various methods which are available for leak detection. Then electromagnetic methods for condition assessment, which include GPR, EM, cable detector, eddy currents. Then we have physical methods which include smoke testing, dye testing, impulse hammer. Then we have visual methods which include man entry and camera inspection. Then we have ultra or infraspectrum, which includes ultrasonic, infrared thermography. And in camera inspection also we have zoom camera, we have CCTV, we have SSCT. Now obviously I will not be able to go in detail of all these methods, but I'll try to show you a glimpse of various methods which are available. First, starting with leak detection. So there is a 3-step strategy for leakage management. First is localize to an area or zone, which is based on flow logging or noise logging. Second is locate, that is leak to within half a meter. Okay, so for which we use noise correlators. And then pinpoint, that is confirmation of the leak position, that for which we can use ground microphone. I'll be showing you all these steps. First is, let's say, localize. So once we do flow logging, let's say this is the minimum night flow, this red line which you see, and all the days of a minimum night flow remains the same. So basically it's an example of daily flow pattern with no serious problem. So this zone does not have any serious problem, and that's why minimum night flow remains at the minimum, has a trend which remains constant over all the days. Now let's go to a zone with serious problem. Okay. So here, for example, average daily flow was 1800 cubic meter per hour, and minimum night flow, this red line was the minimum night flow. we can see minimum light flow also is exceeding, and at the same time average daily flow also is exceeding. So this is a zone with serious problem. So that's how this flow logging helps you isolate the zones where leakage problem might be there. Now this is again district metering, continuous monitoring. One example, this is daily flow pattern, and this is a point of pipe burst, so the flow increases a lot. Again the zone is repaired, so zone returned normal after repair, and again we can see the normal flow coming here. So this is the flow logging concept. Then we have leak noise. So this is the basis of noise correlators, or listening to the leakage noise, which is the next step. Once you have isolated a zone of the leakage, now you are going to locate the leak, as they say. So depending on the backfill, the noise transfer is different. So depending on what is the soil type, your leak transfer to the surface will be different. The pressure within the pipe will affect the quantity of water being lost and the noise generated by the leak. So obviously, if you have high pressure inside the pipe, the leak noise will be higher. That's very easy to understand. And the size of leak will affect the transfer of noise. Again, big leaks will have a different noise, and small leaks will have a different noise. So let's look at this this phenomena. Let's say this is the burst. So energy generated from the leak is transmitted within the pipe through the water. So that's how energy will transfer within the water. Energy from the leak is also transmitted through the pipe wall. So this will also be carried through the pipe wall. Different material type of the pipe again will be giving different kind of signatures of your leakage. So if we talk about different material types which are used, there is steel, ductile iron, copper, asbestos, cement, lead, PVC, polyethylene, and this is the hardest and this is the softest material. Now, leak noise factors, the factors which produce good quality leak noise is high water pressure, hard backfill, small rupture, clean pipes, metallic pipes, and small diameter pipes. So if you have these conditions being met, you will have a very good quality leak noise. Whereas if you have low water pressure, soft backfill, split mains, and crusted pipes, soft lined pipes, and large diameter pipes, your leak noise will be of poor quality. So once we are talking about the noise correlators, or listening to the noise of the pipe, all these factors need to be considered. It's not that you will be able to listen to a good quality leak noise in all the cases. It depends on these factors. Okay. Now there are different levels, 40 dB to 100 dB leak found with noise loggers and usually with conventional methods. 10 dB to 40 dB leak found with noise loggers only, correlation generally required, and 0 dB to 10 dB no leaks. So leaks on plastic pipes are often found at the intensity of 20 to 40. So they can be found only with noise loggers and with correlation requirement. Once we talk about noise correlators, early correlators used to be very, very bulky. Okay, these days it has really changed. They are very small correlators. The basic principle is very simple. You have a transmitter here and you have a transmitter here. This is the leak. You measure the time of the propagation of the leak to both of these, and then you do the cross correlation, and that's why they call correlators, and you are able to pinpoint the location of noise. This is how it looks like. This is, for example, your different connections, and you are able to pinpoint where the leak is happening. Okay. So traditional style transmitters are positioned above the ground. So here you put it above the ground and you put your sensor here, take it inside the appendices and put it there. A wall chamber is left open. Now the cordless kind of transmitters are also there, which can actually be put inside below the ground, and you can actually close this chamber. Okay, so now once you do this, it becomes much more safer because your complete instrument is inside, your chamber is closed, and you can do the monitoring. Then there are ground mics and listening sticks. So this person is, for example, putting this headphone and using a ground mic for listening to the leak. Again, ground mic and listening devices here. So there, once you have located the leak, you can further localize it or pinpoint it using these devices. A leakage engineer locating a leak using a traditional listening stick, where it was directly put on air and the leak was listened to. Then again, this is a ground microphone. So this is a microphone put on the ground and you're listening to the sound which is coming to you from the leak. Now, there is again, there are optical fiber cable based measurements, but in this case, you have to lay the optical fiber with the pipeline at the time of pipeline laying. It's a very effective system where you put the complete optical fiber. This fiber cable itself work as sensor. So fluid or gas leaks and sensing cables provide early detection. It's a very, very good method. It is used for oil and gas pipeline even today, where it is laid with the pipeline, and whenever there is a small leak starting, you get the signal. Okay, so the fiber itself is the sensor, and every meter you can say is a sensor which gives you the leakage position. Now, these are traditional methods like noise correlators, pretty popular, but there are certain cases because of pipe composition, because of low intensity of leakage and other factors which we listed. It's difficult to find the leak with noise correlators. Also, there are cases when, for example, you're not able to find any place to even put your transmitters of the noise correlators. So this is something we call finding the difficult leaks. And that's where GPR comes in picture. So GPR is a technique which is working on the principle of EM reflection. It is sending the electromagnetic impulses into the ground which get reflected from any interface across which there is change in dielectric constant. Now, whenever a leak is happening, it changes the dielectric properties of the soil around it. And that's the basic principle based on which GPR is being used successfully for leak detection. So this is one example which we did at the time of T3 construction. There were this fire hydrant line. These hydrant lines underground. This concrete was laid on top of them, and there were leakage from there. And we used GPR for leak detection there. And nowadays with 3D coming, this is called a heat map. So even heat maps can be created which very clearly tell you which is the zone which has been affected because of leakage. So this is one pipe, this is second pipe, and this is a heat map which has been generated which very clearly tells you which segment of the pipe is responsible for this leakage. This is again a GPR image showing water accumulation from the leak. So this is water accumulation which has taken place because of leak. Another example, so GPR data before and after interpretation of image was this. So this was basically one pipe, and this is a truncated pipe here. This is a fractured main, and this is a leakage zone, and this is again a leakage zone. These two are the leakage zone from this fractured main. So this is the data which you receive. Of course, you have to interpret this data like this, and then you know the leakage zones. We did a lot of experimental work with the university on finding out these water leaks from water mains. This was in the city of Bangalore, and you can see we have collected different kind of signatures. So this is high amplitude reflections from saturated layer top. So all this work was done parallel to the water main. So we knew where the water main is. We first located the water main and we did the work parallel to that. So this is, you can see this is the traces or distance. So we know at what particular point the leakage from the pipe has taken place because it is creating a saturated layer top there. Different kind of soils will have different kind of signatures. So again, this is a strong amplitude from water saturated layer top here. In this area, on the other hand, it is loss of signal due to increased conductivity caused by water saturation. So depending on kind of soil it is, you can have different signatures, and you need experience to interpret this, of course, but this is another signature of water leakage. Here, faded zone due to water saturation, it is called frequency filtering. Again, you know, so we are going parallel to the pipeline and we know exactly at what location the pipeline is leaking. This is an example of an area where the pipe was not holding any pressure. So first we did GPR data in affected area before water injection. Then we did the water injection. So GPR data in affected area after water injection. Note the deep feature between 11 meters to 16.5 meters disappears. So this is 10 meters. So this is a deep feature here. 11 meters to 16.5 meters. In this, it's not there. This is due to signal attenuation in the moist soil. So this basically proves that this is the area from where the leakage is taking place, because all other areas, both are exact replica of each other except this area where this reflection simply disappears. So that means the water injection has affected the conductivity of this particular area. There is another method to find difficult leaks, and that is based on acoustic. So we put geophones all along the pipeline. So these are geophones all along the pipeline. Like I had shown you earlier, this ground listening devices. So this is just a modern version of that. Instead of just having one device, you have 24 devices. So 24 geophones or 48 geophones you can put together. Rather than putting it in your ear, let the machine do the listening. So these are the geophones which have been put all along, and now wherever the leak is, you see the signature in the machine. So this is the distance, for example, at which the leak is taking place. And a very, very strong method. Now there are a few very interesting methods which have come up. One is smart ball technique. I'll just show a small video of this.
Smart ball technology is an innovative acoustic leak detection tool for pipelines, 4 inches in diameter and larger. The tool consists of an instrumented aluminum core housed within a urethane or foam shell. The Smart Ball inspection tool can be easily deployed and retrieved using existing pigging facilities. In non-piggable lines, the tool can be launched using standard off-the-shelf fittings. Once inside the pipeline, Smart Ball easily rolls along the bottom of the pipe as it is propelled by the product flow. Since Smart Ball isn't a full-bore tool, it can easily navigate any bends within the line. Smart Ball can be tracked using surface mount sensors, typically placed on block or check valves, as well as using above-ground markers placed at selected surveyed points. As the Smart Ball navigates the line, it continuously records acoustic data. As it approaches a leak, a very distinct noise signature can be heard. Smart Ball has been able to detect leaks as low as 0.03 gallons per minute. Once the Smart Ball has completed the inspection, it is easily removed from the line. Smart Ball is ideal for long inspection runs, as the onboard battery can last several hundred hours.
So very, very interesting tools are coming up, and Smart Ball actually is not very new. It is being used. If you need more details about it, please write to me. I'll love to share. Now I'll very briefly talk about other condition assessment tools. So one is smoke testing, right? So in this, we force a smoke-filled air through a sewer line. The pressurized smoke will fill the main line and any other connections, then follow the path of the leak to the ground surface. So this is one way to find out leakages in sewer lines, smoke testing. Then there is dye testing. So dye testing with a non-toxic dye is used to confirm rain or ground entry points into the sanitary sewer system. Dyed water is introduced, roof drain leaders, driveway drains or area drains. In some instances, dyed water is injected into the ground around foundations to check for the illegal connections of foundation drains. After introducing the dyed water, the downstream sanitary sewer manhole is checked, and if a clean out is present, it is checked for presence of dyed water. Dye testing is one way of helping to determine whether a pipe or a structure drained if it is not obvious by observation or shown on existing plan records. Dye testing can help identify inappropriate connections also. Then we have CCTV. Most of you will be familiar with this. So this technology uses a television camera mounted on a remotely controlled self-propelled robotic device that is connected to a video monitor, a video cassette recorder and other recording devices by a long electric cable to inspect sewer lines. The robotic system is placed directly into the sewer through a manhole. Once inside the sewer line, the remote controlled device moves through the sewers and allows the operator to examine the entire length of pipeline between two manholes. The CCTV system relays live footage to a high-resolution monitor located in a mobile survey unit. The footage of pipeline surveyed is recorded on videotape. If a defect is detected, the operator can stop the camera and investigate the defect in more details. In fact, lately there have been a lot of development on CCTV technology, and so many different kind of systems are available now. Then we have radiometric probes, which uses neutron and gamma ray backscatter probes for detection of cracks. Passing a joint or a cavity behind the pipe with the probe, the counting rate of the backscattered counts changes in a typical way. So this is another technique which is used for pipeline condition assessment. We have current probes, which are geoelectric sensors, measures variations in ground resistivity, and it's also used to detect the leak points. Again, we have electromagnetics, which measures wall thickness of a pipe by sensing the attenuation and phase delay of EM signal which is passed through the pipe wall. With this, I come to conclusion of this session. I have tried to cover up practically a lot of things in a very short time, but I'm always available to answer your questions, and these are my contact details. Please feel free to write to me if you want to understand more on any of these aspects which we have discussed in this presentation.